everyone, this is Miss Moriarty, and I'm here to discuss with us our notes on concept number 1. As we watch the video, you want to make sure that you are taking down notes using the follow-along notes given to you in class. At the end of this video, please make sure that you mark it as done and go back through your notes and remember, take a look, come up with your active recall questions, and provide to me a summary on our concept number 1. So here we go. So here, right, in the organization of life, we've discussed now that cells are the most basic unit of life, but there's actually things that are even smaller than that. And here we can see matter. This is anything that has mass, occupies space, and is comprised of atoms. And it is an atom that is the smallest part of any element that still has its properties of that element. And so atoms are usually classified as the smallest unit of matter. It is these atoms that comprise then elements, and it's these then elements that help to make up life. The following 6 elements are necessary for life. Things like carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. The combination of these 6 elements make compounds and other molecules that are required for our survival and help to make and build cells. Now, looking at an atom, we can break down its structure into 3 subatomic particles, one being its protons found in its nucleus, neutrons also found in the nucleus, and electrons that kind of surround it in what's called the electron cloud. You'll notice each of these subatomic particles have a charge. Protons are positive in charge, electrons are negative in charge, and neutrons are neutral in charge. Here's a nice little diagram showing us here. Here's our nucleus of our atom comprised of our protons and neutrons here. Here's our electrons that float in the cloud there. And it is the number of neutrons and number of protons we find in the atom creates its mass number. And so if you ever want to find out how many protons an element may have, if you look at the periodic table of elements, you can take a look at its atomic number. That will tell you the number of protons, but the number of mass number would be number of neutrons and protons. Now, a chemical element is going to be a pure substance that consists entirely of just one type of atom. And atoms of the same element that have different numbers of neutrons are known as an isotope. Now, although isotopes have different masses, they're still going to have the same chemical properties because they will still have the same number of protons. So the common example is like carbon-12 versus carbon-13. They have the same number of protons, but different numbers of neutrons, but maintain the same chemical properties. Now, in nature, most of those elements we find combined with other elements in what's called a compound. A compound is a substance formed by the chemical composition of 2 or more elements in a definitive proportion. So the example here would be that water contains 2 atoms of hydrogen and 1 atom of oxygen and has the chemical formula of H2O. Now, when that bond formation occurs, it's actually what's called the valence electrons, or the electrons that are in the outermost shell of our atoms that actually are involved in the bonding process. There are 2 types of bonds I would like us to know, and that is an ionic bond and a covalent bond. Now, what forces these bonds to happen? What forces these electrons to either be shared or transferred between different elements? That is the atom's electronegativity. The definition of electronegativity is the tendency for an atom to attract electrons to itself, especially when it's covalently bonded to another atom. The more electronegative an atom might be, the stronger it pulls electrons towards itself. On the periodic table of elements, the elements that are found in the top right-hand corner of the periodic table, excluding the noble gases, have the greatest electronegativity. And we can see that here in this image. So as we move from left to right, we can see that as we move across the periodic table of elements, the stronger the pull of electrons is going to be. And take note, we're really going to focus on oxygen here, because the next topic we're going to discuss is properties of water, and it's really important to note that we know that oxygen is much more electronegative than, say, hydrogen. Now, what about when two elements bond ionically? This is when one or more electrons are transferred from one atom to another. So a neutral atom, which has the same number of protons versus electrons, will actually lose an electron and become positively charged, while another neutral atom will gain an electron and become negatively charged. When we see that happen, a neutral atom that loses the electron and becomes positive, it's called a cation, while an atom that gains an electron and becomes negative becomes an anion. Those positive and negative charged elements are then known as ions. And here's a classic example. Right, when we look at table salt or sodium chloride, how they bond to one another is that an electron will be lost by our sodium in the outer shell, while chlorine, which is more electronegative, will gain an electron and become a chloride ion. Those oppositely charged ions have strong attractions to one another, forming what we know as an ionic bond. But in a covalent bond, this is when electrons are shared between atoms. So not transferred, shared. And the structure that results when atoms are joined together by a covalent bond is known as a molecule. The molecule is going to be the smallest unit of most compounds. We see in the right-hand side, this is actually a water molecule, and we can see that the oxygen and two hydrogens are going to be covalently bonded. And you'll notice that this creates somewhat of a charge on our atoms. Now, another type of bond that we need to know, especially when discussing properties of water, will be these weak attractions known as hydrogen bonds. These bonds form between specifically a hydrogen atom of one molecule and either maybe an oxygen or a nitrogen atom of a neighboring molecule. And these are very weak attractions because of oppositely charged atoms. And so these weak attractions can break. And so here, I'm just going to add a little bit more to our video here in concept number 2. We're going to be discussing the properties of water. And so previously stated, we know water is H2O. We know it's a molecule made up of two atoms of hydrogen and one atom of oxygen. We know that it's critical for all life processes and has a very special property, mostly due to the fact that we consider it to be a polar molecule. Now, what does that mean? A polar molecule is a molecule that's bonded covalently and has unequal distribution of charges. So meaning one side of the molecule might be positive, while the other side is slightly more negative. Typically, molecules that are polar actually dissolve in water, and a classic example would be water. A nonpolar molecule, however, is still bonded covalently, except this time there is no separation of charge. There's no positive or no negative poles that are formed within the molecule itself. Because of that, it does not dissolve in water very easily. Some examples might be carbon dioxide, oxygen gas, and lipids or fats. But here's just some more examples of what I mean by that. So we can see here water, H2O, because oxygen, as we mentioned previously in the video, is really electronegative, right? It's more electronegative than hydrogen atoms. Because of that, it pulls electrons closer to its nucleus, creating a slightly negative pull. When it does that, the hydrogens, as a result, become slightly positive. We could see here in ammonia, this is another example of a polar molecule. Our nitrogen is more electronegative than our hydrogen atoms, so it pulls electrons closer to its nucleus, creating slightly negative charges, versus the hydrogens that have slightly positive charges. But looking at our nonpolar molecules, right, our carbon dioxide, because they're equal, because neither one is more electronegative than the other, we can see that there are no charges found in this molecule. And we see the same thing in our methane molecule. All right, everybody, this is the end of the video. You want to make sure that you took down your notes. Please mark this assignment as done on Classroom, and please write your questions and summaries on your notes.